Silent data corruption, or SDC, has been a challenging issue facing the hyperscaler data centers. Hundreds and thousands of servers are co-located in a single building that spans multiple football fields, creating environmental conditions that result in silicon failures. These failures are hard to mimic during ATE testing. For example, they show up when AI/ML training applications are continuously running for weeks or months, and the ICs are expected to be stressed with varying level of software workloads. SDC-related failures are never visible through traditional means such as diagnostic tools or logs, but manifest as application failures that are caught much later. Such failures may result in the loss of data, lack of access, or disruption of services, forcing system companies running data centers to divert their workloads, shut them down, or even risk losing user trust. This results in significant business applications, often in billions of dollars. With miniaturization and introduction of new technologies such as gate-all-around and nanosheet transistors, the exposure of subtle defects that may result from the physical imperfections during silicon manufacturing can't be overstated. There are multiple reasons for SDC-related failures in large-scale systems. First, there can be certain latent defects that remain hidden due to inadequate testing of the transistors post-manufacturing. Second, our ability to replicate environmental factors such as power, voltage, temperature, and software workloads in an ATE environment are quite limited. These constrain us from being able to test silicon and eradicate such intermittent defects. Third, with lower process technology nodes, our ability to model on-chip process variations are quite limited. Therefore, it requires adequate compensation using design and test margins to meet the required performance metrics. Finally, when running demanding workloads for AI/ML applications, which run 24/7 for months, cause accelerated silicon aging that is hard to reconcile and predict in reliability modeling. All these factors results in test escapes, meaning we are unable to eradicate borderline ICs in field, causing computational malfunction showing up as large-scale system application failures. The consensus across the industry that the occurrence of SDC is a consequence of physical defects in silicon is a wake-up call to improve the overall test quality. We at Siemens EDA believe that a multi-pronged effort will be needed across the industry to bring down SDC-related failures. Not only do we need to improve test quality to reduce test escapes, on-chip test and monitoring capabilities are also needed to continuously evaluate how silicon is performing, thereby preventing failures. Let me now explain some of the mitigation strategies that we are looking at. First, let's talk about the overall methodology to test delay defects that is widely used across the industry. Most of the companies rely heavily on the conventional transition fault model that targets primarily gross delay type of failures. Although defect models such as timing error and cell-aware timing error are gaining momentum, they rely on single input switching, meaning a transition is allowed to propagate through only one input while the other inputs are held at a non-controlling constant value. However, we all know that SIS doesn't necessarily mimic how an IC operates in functional mode. Additionally, literature shows that multiple input switching can result in larger propagation delays compared to SIS. In other words, preventing miss results in inadequate testing of the path delays, leaving room for small delay defects to escape. Another factor that is greatly overlooked is the improper integration of current test methodologies into a multi-corner, multi-mode design paradigm, where delay defects must be targeted under different PVD corners and test patterns optimized to work across all such corners. Only this way will we be able to close the gap with the operating conditions an IC is subjected to when running in system. Second, conventional stress test methodologies that are dependent on burn-in or voltage-related tests are falling short of eradicating latent defects that show up as early life failures. Whether one is using EVS or DVS or H-tall testing, most companies today rely on either toggle coverage or ad hoc methods to generate patterns without ways to measure their impact on the overall test quality. We strongly believe that intelligent voltage and current based stress test solutions are necessary. Alongside this, the ability to measure and report how each and every transistor in the design is getting stressed is central to improving the quality of tests. Once we have the ability to measure stress test coverage, smart ATPG techniques can be developed to cover the holes to guarantee a more holistic coverage of the entire design. Accordingly, we have been working on developing an activity-based and a defect-based stress test model that would allow us to simulate and measure the behavior of transistors under stress and generate patterns that would activate the conditions that are necessary to stress every transistor in the design. Third, despite trying our best to improve the overall test quality, we realize that it will be very difficult to mimic the environmental conditions in a data center environment. Consequently, in addition to continuously improving the overall test quality for the shipped parts, we need to provide a DFT infrastructure that would enable one to apply the manufacturing test patterns in field, thereby allowing one to achieve similar levels of test quality as and when needed. Historically, logic-based has been deployed for automotive and networking devices to monitor the quality of such devices in field. But the demands on in-field test quality have not been stringent enough and therefore were adequately serviced by logic-based. With SDC type of failures in data centers, test quality can't be compromised. We need to enable the application of all types of deterministic patterns in field, either during periodic maintenance or opportunistically when the system is still in operation. The goal is to quickly identify failing parts in field and allow one to either harvest such parts or take them off completely from operation. Our in-system test controller, along with test compress and streaming scan network technologies, enable our customers to continue using the manufacturing test infrastructure for in-system in-field test and diagnosis. As we speak, this is being deployed by major data center companies to apply structural tests in addition to the functional tests used for periodic testing of their servers. Finally, as we all know, complex semiconductor designs rely heavily on functional, environmental, and structural monitors and sensors that are embedded throughout the design. But due to lack of good on-chip infrastructure, limited ability to observe sensors during structural and functional modes of operation, and lack of correlation of sensor data between functional versus test modes, the usage of sensor data in field has been very limited. This needs to change. As we move towards angstrom technology nodes, our ability to accurately model on-chip variations or develop good reliability models is becoming very difficult. Therefore, the usage of sensor data will be key to predict the behavior of silicon. This would enable system companies to predict how close silicon is from failing, monitor how silicon is aging in field, and selectively upgrade parts rather than whole-scale upgrading of servers every certain number of years. This opens up avenues for rapid adoption of adaptive testing, where structural patterns can be used to mimic mission mode behavior of the design. The type of test patterns or the type of defect models that need to be targeted can be adapted based on how closely the structural tests correlate with the functional behavior of the design. In summary, as you can comprehend, a variety of techniques will ultimately enable silicon health monitoring, which we believe will be critical to minimize any disruption it would otherwise cause. In turn, it will save billions of dollars and improve the overall testability, safety, and security of semiconductor devices.